Tonight, we're going to talk about a star so enormous that it breaks your ability to imagine size. Betelgeuse. You've probably heard of it. The bright reddish star in the constellation Orion. But here's what most people don't understand. Betelgeuse is so large that if you placed it where our sun is right now, the Earth wouldn't just be close to it. The Earth would be deep inside it. So would Mars. So would Jupiter. This star is so large that its outer edge would stretch far beyond Mars, swallow the asteroid belt, and reach toward Jupiter's orbit. And here's the part that should genuinely unsettle you. Stars this big don't just burn out. They don't fade quietly. They die in one of the most violent events the universe is capable of producing. And Betelgeuse is getting close. Before we go any further, if you find this kind of deep exploration fascinating, a quick like or subscribe really helps the channel grow. It's a small thing for you, but it makes a huge difference for me. Now, let's begin. Let's start with something you can see with your own eyes. On a clear winter night, if you step outside and look toward the south, you'll notice one of the most recognizable patterns in the entire sky. The constellation Orion, the Hunter. 3 bright stars in a neat diagonal line form Orion's belt. People have been looking at it for thousands of years. Ancient Egyptians associate it with Osiris. The Greeks saw a mighty hunter placed among the stars by the gods. Nearly every civilization in history has had a name and a story for this arrangement of stars. You don't need a telescope, you just need your eyes and a reasonably dark sky. Now look at Orion's upper left shoulder. You'll see a star that looks noticeably different from the others. While most of the bright stars in Orion shine white or blue-white, this one glows with a deep reddish-orange color. It stands out immediately once you know where to look. That star is Betelgeuse, and it is one of the most extraordinary objects you will ever see without a telescope. Betelgeuse is what astronomers call a red supergiant. That classification alone should tell you something remarkable is happening. This isn't an ordinary star. It's not like our sun, a stable middle-aged star steadily burning hydrogen in its core. Betelgeuse is something fundamentally different. It is a star in the late stages of its life, swollen to dimensions so extreme that when you actually work through the numbers, your sense of scale simply stops functioning. Most people have heard that Betelgeuse is big and leave it at that. But big doesn't begin to capture what we're talking about. We need to understand exactly how large this star is, step by step, comparison by comparison, because once you truly grasp its size, everything else about its story, its instability, its wild behavior, its inevitable violent death, all of it follows directly from that one staggering fact. But before we can appreciate how enormous Betelgeuse is, we need to start with something we know. We need to start with the sun. The sun is big. From our perspective here on the surface of Earth, the sun seems like a modest glowing disk hanging in the sky, about the same apparent size as the moon. But that appearance is deceiving. The sun is a massive ball of plasma with a diameter of about 864,000 miles. That's roughly 1,400,000 kilometers. This is so large that it overwhelms most comparisons we try to make. If you could somehow drive a car at highway speed around the sun's equator, it would take you over 5.5 years of continuous driving. No rest stops, no sleeping, just constant driving for more than 5 years to make one loop around the sun's middle. Now, let's bring Earth into the picture. Earth has a diameter of about 7,926 miles. You could fit about 109 Earths side by side across the diameter of the sun, 109 Earths in a straight line to match the width of the Sun. And if you wanted to fill the Sun's interior with Earths, if you could somehow pack Earth-sized spheres into that enormous volume, you would need approximately 1,300,000 of them. 1,300,000 Earths to fill the space occupied by one star, our star, the ordinary yellow dwarf we see every day. Think about what that means. Every mountain, every ocean, every city, every forest, every person who has ever lived, all of human history, all of it happened on a planet that you would need 1,300,000 copies of just to fill the interior of the Sun. And the Sun is not a particularly large star. It's not small, but it's not exceptional either. It's a medium-sized star, what astronomers classify as a G-type main sequence star. In the grand catalogue of stars across our galaxy, the Sun is thoroughly ordinary. It's average in mass, average in temperature, average in brightness. This is our baseline. This is what a normal star looks like. Remember this, because we're about to leave normal behind entirely. The Sun sits about 93 million miles from Earth. This distance is so fundamental to astronomy that it has its own name, one astronomical unit. Light from the Sun takes about 8 minutes and 20 seconds to travel this distance. If the Sun suddenly vanished, you wouldn't know for over 8 minutes. And from that distance, the Sun appears as a modest disk in the sky. Something you can blot out with your thumb held at arm's length. But we've just established that this modest disk is actually a sphere so enormous that over 1 million Earths could fit inside it. This is the first lesson of cosmic scale. Things that seem small are often unimaginably large when you actually understand the distances involved. And things that seem large, well, there's always something larger. Now, let's turn our attention back to Betelgeuse, and this is where the numbers start to leave the realm of anything you've experienced in your everyday life. Betelgeuse is a red supergiant star located in the constellation Orion, about 550 light years from Earth. That's far enough that the light entering your eye when you look at Betelgeuse tonight left that star around the time of the Italian Renaissance, centuries before anyone alive today was born. But despite being 550 light years away, Betelgeuse is still one of the brightest stars in our sky. It's typically the 10th or 11th brightest star visible from Earth, though its brightness varies because Betelgeuse is what astronomers call a variable star. It dims and brightens over time, sometimes noticeably, which we'll explore later. But the fact that it's visible at all from such an enormous distance tells you something important. This star is pouring out an almost incomprehensible amount of light. Betelgeuse is roughly 100,000 times more luminous than the Sun. 100,000 times. If you replace the Sun with Betelgeuse, the amount of energy hitting Earth would be so extreme that the planet would be vaporized almost instantly. But we wouldn't be around to experience that, because Earth would already be inside the star. This is the fact that changes everything. Betelgeuse is so large that if you placed it at the center of our solar system, right where the Sun is now, its surface would extend far beyond the orbit of Earth. It would swallow Mercury. It would swallow Venus. It would swallow Earth. It would swallow Mars. And it would keep going, pushing out into the asteroid belt, past most of the rocky debris between Mars and Jupiter. Recent estimates place Betelgeuse's radius at somewhere between roughly 700 and possibly over 1,000 times the radius of the Sun. The uncertainty exists because measuring the exact size of a star like Betelgeuse is genuinely difficult. The star doesn't have a hard surface. It has no sharp edge. Its outer layers are so diffuse that they fade gradually into space, making it hard to define exactly where the star ends and where empty space begins. But even using the more conservative estimates, the picture is staggering. At around 760 solar radii, which is one of the most widely cited modern measurements, Betelgeuse's surface would sit at roughly 3.5 astronomical units from the center. Mars orbits at about 1.5 astronomical units. The asteroid belt extends from roughly 2 to 3.5 astronomical units. So at this estimate, Betelgeuse would engulf Mars entirely and reach into the outer parts of the asteroid belt. At the higher estimates, exceeding 1,000 solar radii, the surface could approach 4.5 astronomical units or more, reaching toward Jupiter's orbital distance. Let's walk through this slowly, because the full picture deserves to be understood one planet at a time. Mercury, the innermost planet of our solar system, orbits the Sun at an average distance of about 36 million miles. That's roughly 1/3 of an astronomical unit. Mercury would be deep inside Betelgeuse, not near the surface, not close to the edge. Mercury would be buried hundreds of millions of miles beneath the outer layers of the star. It would simply cease to exist, consumed entirely. Venus orbits at about 67 million miles from the Sun, roughly 7/10 of an astronomical unit. Venus too would be well within the interior of Betelgeuse. The planet, famous for its crushing atmosphere and surface temperatures hot enough to melt, lead would itself be vaporized inside a star, where those temperatures are utterly trivial compared to what surrounds them. Earth, our home, orbits at 93 million miles, 1 astronomical unit, inside Betelgeuse, not close to the surface, not near any edge. Earth at this position would be surrounded on all sides by hundreds of millions of miles of stellar material extending outward in every direction. Everything we know, every human who has ever lived, every ocean and mountain and forest and city, all of it would be inside this star with room to spare in every direction. The Sun we orbit is massive compared to Earth, but Betelgeuse makes the Sun look like a marble sitting at the center of a concert hall. Mars orbits at about 142 million miles, roughly 1.5 astronomical units. Mars would also be consumed. The red planet would be inside Betelgeuse and not near the surface either. At the more conservative size estimates, Mars sits roughly in the inner third of the star. At the higher estimates, Mars is buried even deeper. Beyond Mars, the asteroid belt stretches from about 2 astronomical units to roughly 3.5 astronomical units from the center of the solar system. This is where things start to depend on which size estimate you use. At the lower estimates, Betelgeuse's surface falls somewhere in the outer asteroid belt. At the higher estimates, the star extends past the asteroid belt entirely and pushes toward the orbit of Jupiter at 5.2 astronomical units. Either way, the result is the same in emotional terms. Betelgeuse is so large that the first 4 planets of our solar system, the ones we think of as the inner solar system, would all be gone, completely enveloped, not orbiting the star, inside the star. Let me put this another way, because the orbital distances, while accurate, can feel abstract. The diameter of Betelgeuse, using a moderate estimate of roughly 700 times the Sun's diameter, is approximately 600 million miles. 600 million miles across. If you could somehow board a commercial aircraft and fly across Betelgeuse at typical cruising speed, about 550 miles per hour, That flight would take you over 124 years. You would be born on that airplane, live your entire life on that airplane, die on that airplane, and your great-grandchildren would still be flying, still not having reached the other side of this single star. Compare that to flying across the sun, which would take about 65 days at the same speed. Betelgeuse is on a completely different scale. Now let's talk about volume, because diameter only tells part of the story. Volume scales with the cube of the diameter. That means when you double the diameter of a sphere, you don't just double the volume, you multiply it by 8. When you increase the diameter by a factor of 700, the volume increases by 700 cubed. That number is 343 million. So Betelgeuse's volume is roughly 343 million times the volume of the Sun. And since the Sun's volume is already 1,300,000 times that of Earth, the volume of Betelgeuse compared to Earth is almost beyond language. You would need somewhere around 450 trillion Earths to fill the interior of Betelgeuse. Let me say that again because it deserves to land. 450 trillion Earths. Every single one of those is a full-size planet, 8,000 miles across, oceans, continents, mountains, and you would need 450 trillion of them packed together just to occupy the same volume as one star. This is the scale we're dealing with. This is what's hanging there in Orion's shoulder every winter night, visible to the naked eye, glowing reddish-orange above the rooftops. But here's what makes Betelgeuse even stranger. Despite its almost unthinkable size, Betelgeuse is not particularly massive compared to what you might expect. It contains only about 15 to 20 times the mass of the Sun. That might sound like a lot, and it is a lot by human standards, but think about what that means in context. The Sun's volume multiplied by 343 million gives you Betelgeuse's volume, but the mass is only multiplied by 15 to 20. This tells you something profound about the physical state of this star. Betelgeuse is extraordinarily diffuse. Its outer layers are spread so thin across such an enormous volume that in many regions, the density of the star's material is lower than what most people would consider a vacuum. The outermost regions of Betelgeuse are thinner than the vacuum inside a standard vacuum chamber, the kind used in industrial manufacturing or university physics labs. Think about that for a moment. Parts of Betelgeuse, a star, a real burning star visible in the night sky, are emptier than the inside of a vacuum pump. If you could somehow scoop up a cubic meter of material from the outer regions of Betelgeuse and bring it back to Earth, you would essentially be holding nothing. The gas would be so tenuous, so sparse that for all practical purposes you'd be holding empty space with a faint trace of hydrogen and helium atoms scattered through it. You could wave your hand through it and feel nothing, and yet this nearly empty gas is part of a star. It's glowing, it's radiating energy. It's held in place by gravity, loosely, barely, but held. The outer envelope of Betelgeuse is more like a vast luminous fog than anything you'd normally think of as a solid or even a dense gas. The core is a very different story, incredibly dense and hot, but the outer layers are ghostly. This low density is directly related to the star's enormous size. Betelgeuse hasn't gained hundreds of millions of times more mass than the Sun. It has taken a relatively modest amount of mass, 15 to 20 times the Sun's worth, and puffed it out across a volume hundreds of millions of times larger than the Sun. The mass is spread thin. Imagine taking a balloon and inflating it far beyond what it was designed for. The rubber stretches thinner and thinner. The balloon gets bigger and bigger, but the amount of rubber hasn't changed. It's just spread across a much larger surface. Betelgeuse is doing something similar with its outer layers. The material is still there, but it's spread so thin that the boundary between star and space becomes blurry. In a real sense, Betelgeuse doesn't have a surface the way Earth has a surface, or even the way the Sun has a visible surface. Its outer atmosphere just gradually fades into the interstellar medium. The star doesn't end so much as it evaporates. Now, you might wonder how we can possibly know all of this. How do astronomers measure the size of a star that is 550 light years away? Even through the most powerful telescopes, most stars appear as nothing more than points of light. You can magnify them as much as you want, use the biggest mirror ever built, and they remain points. The distances are simply too great and the stars too small, even enormous ones, for their disks to be resolved through ordinary telescopes. A star would need to be vastly closer or vastly larger than average for any telescope to see it as more than a dot. Betelgeuse happens to be both relatively close and extraordinarily large, and that combination makes it one of the most important stars in the history of observational astronomy. Because Betelgeuse is one of the very first stars whose actual surface was directly imaged, not as a dot, as a disk, a resolved circle with visible features on it. The first measurement of Betelgeuse's angular diameter was made all the way back in 1920 by Albert Michelson and Francis Pease using an interferometer mounted on the 100-inch telescope at Mount Wilson Observatory in California. Interferometry is a technique that combines light from two or more separated points to achieve resolution far sharper than any single telescope could manage on its own. By measuring how the light waves from Betelgeuse interfered with each other, Michelson and Pease were able to determine the star's apparent angular size on the sky. The result was tiny, about 47 milliseconds, a measurement so small that it's difficult to convey how fine it is. An arcsecond is 1/3600th of a degree. A millisecond is 1,000th of that. 47 milliseconds is roughly equivalent to the apparent size of a tennis ball, seen from a distance of about 180 miles. And yet, this minuscule angle, combined with a distance estimate, gave the first real measurement of Betelgeuse's physical diameter. Even with the limited precision of early 20th century instruments, the result was stunning. Betelgeuse was enormous, far larger than anyone had expected for a single star. Since then, the measurements have become dramatically more refined. Modern interferometric instruments, particularly the VLTI at the European Southern Observatory in Chile, have not only measured Betelgeuse's diameter with far greater precision, but have actually produced images of the star's surface. Real images, not artists' impressions, not simulations, actual photographs showing the face of a star hundreds of light years away. What these images reveal is astonishing. Betelgeuse's surface is not smooth and uniform like the Sun appears in basic photographs. It is covered in enormous convective cells, vast regions where hot material from deep inside the star rises to the surface, radiates its energy, cools, and sinks back down. These convective cells on Betelgeuse are not small features. Individual cells can be nearly as large as the entire orbit of Earth around the Sun. They are continent-sized features, if your continent happened to be 100 million miles across. The surface of Betelgeuse is churning, boiling, heaving with these massive convective plumes that constantly reshape the star's appearance. The Hubble Space Telescope produced one of the first ultraviolet images of Betelgeuse's disk back in 1996, revealing a massive, bright hotspot on its surface. That single hotspot spanned a significant fraction of the stellar disk, stretching tens of millions of miles across. A single bright patch on the face of a star, larger than the distance from Earth to the Sun. Later observations using ground-based interferometry showed multiple hotspots and asymmetries, regions where the star's surface was noticeably brighter or dimmer. These observations confirmed something important. Betelgeuse is not a static object. It is dynamic, constantly changing, its surface reshuffling as enormous currents of superheated gas churn beneath it. This surface activity is directly connected to the star's enormous size. In the Sun, convective cells are relatively small. The granulation pattern visible on the Sun's surface consists of cells roughly 1,000 kilometers across, each one lasting about 10 to 20 minutes before it dissipates and is replaced by another. The Sun has millions of these tiny cells covering its surface at any given time, but in Betelgeuse, the convective zone extends much deeper into the star, and the star itself is so much larger that the convective cells scale up accordingly. Instead of millions of small cells, Betelgeuse has perhaps only a handful of enormous ones, each one spanning a significant fraction of the star's diameter. This is sometimes called the problem of giant convection, and it's one of the reasons Betelgeuse's surface appears so lumpy and asymmetric in images. The churning is happening on a scale so vast that individual plumes of rising gas can distort the overall shape of the star. These same convective motions are responsible for lifting material from deep inside the star up to the surface and occasionally beyond, ejecting it into space. The mass loss that Betelgeuse experiences, shedding material into its surroundings at a rate that far exceeds anything the Sun does, is driven in large part by these enormous convective plumes. Hot gas rises from the interior, reaches the tenuous outer layers where gravity's hold is weakest, and gets flung outward into space. Over thousands of years, this process has surrounded Betelgeuse with shells and arcs of expelled material extending many times the star's own diameter into the surrounding space. These structures have been imaged in infrared light, and they tell the story of a star that has been slowly shedding its outer layers for millennia. So when we talk about Betelgeuse's size, we are not relying on guesswork or indirect inference. We have measured it. We have photographed it. We have watched its surface change in real time across decades of observation. Betelgeuse is one of the best studied stars in the entire sky, precisely because its combination of enormous physical size and relative proximity to Earth makes it one of the only stars we can resolve as more than a dot. This is not the behavior of a healthy star. A stable star like the Sun is in a state of equilibrium. Gravity pulls the star's mass inward, trying to collapse it. The energy generated by nuclear fusion in the core pushes outward, resisting the collapse. These two forces balance each other, and the star maintains a steady size for billions of years. The Sun has been roughly the same size for 4.5 billion years, and it will remain roughly the same size for another 5 billion years. That's stability. That's a star in the prime of its life, burning hydrogen at a sustainable rate, neither expanding nor contracting. Betelgeuse is not in equilibrium in the same comfortable way. Its extreme bloated state tells us that something has changed deep inside the star. The internal structure of Betelgeuse is fundamentally different from the Sun's internal structure. The processes occurring in its core have shifted. The fuel sources have changed. The balance between gravity and radiation pressure is being maintained, but only barely, and not in the clean, stable way the Sun manages it. Betelgeuse pulsates. Its brightness changes, its size fluctuates. The star is restless in a way the Sun is not. Material from its surface is being shed into space constantly. Betelgeuse is surrounded by enormous clouds and shells of gas that is ejected over the course of thousands of years. The star is literally losing itself, bleeding mass into the void. This instability is not random, it's not a fluke, it is the direct and inevitable consequence of how large and massive this star is. Betelgeuse didn't become a red supergiant by accident. It followed a path dictated by the laws of physics, a path that every star of similar mass will follow. The size of Betelgeuse is not just a curiosity, it is a signal that tells astronomers exactly where this star is in its life cycle. And it tells them something else too. Something more ominous. Stars that reach this state, stars that swell to these unimaginable dimensions, do not stay this way forever. They cannot. The physics will not allow it. A star this large, this bloated, this unstable, is approaching an endpoint. And the endpoint for a red supergiant is not a gentle fading. It is not a slow cooling. It is one of the most violent events the universe is capable of producing. Betelgeuse sits there in Orion's shoulder every winter, looking calm and steady to your eyes, a reddish point of light, barely distinguishable from the other bright stars unless you know what to look for. But behind that calm appearance is a star in crisis, a star whose dimensions defy ordinary comprehension. A star so large that entire planetary orbits fit inside it. A star whose outer layers are thinner than a laboratory vacuum and whose core is undergoing processes that are driving it toward something catastrophic. And to understand what that catastrophe will look like and why it's inevitable, we need to understand something deeper. We need to understand what's happening inside Betelgeuse right now. What's burning in its core, why the fuel it's using matters, and why mass, the same mass that makes Betelgeuse so large, is also what guarantees it will die in the most spectacular way a star can die. The size of Betelgeuse is not separate from its fate. They are the same story. The enormity of this star and the violence of its death are two expressions of the same underlying reality. Mass dictates everything in the life of a star. How bright it shines, how long it lives, how large it grows, and how it dies. Betelgeuse has the mass to become enormous, and that same mass has set it on a path toward an ending that will be visible across the galaxy. To understand that ending, we first need to understand how stars like Betelgeuse burn through their fuel and why they burn through it so much faster than quieter stars like the Sun. Because the speed at which a star consumes its fuel is not proportional to its mass. It's far worse than that. And that difference, that brutal mathematical relationship between mass and fuel consumption, is what makes supergiant stars the shortest lived and most dramatic objects in the stellar universe. We've established something extraordinary so far on this journey. Betelgeuse is so enormous that if you placed it at the center of our solar system, it would swallow every planet out past Mars and possibly reach into the neighborhood of Jupiter. Its volume is hundreds of millions of times larger than the Sun's, and yet its mass is only about 15 to 20 times greater. That combination of extreme size and moderate mass tells us something critical. Betelgeuse is bloated, distended, swollen far beyond what a healthy star in the prime of its life would ever be. And that immediately raises a question. How did Betelgeuse get this way? What happened to turn a star into something this enormous and this unstable? The answer takes us deep into the physics of how stars live and die. And it reveals something that might surprise you. Betelgeuse wasn't always like this. It wasn't born a red supergiant. In fact, it was born looking nothing like what you see in the sky tonight. And the story of how it transformed from what it once was into what it is now is really the story of how mass controls everything about a star's existence. Let's go back to the beginning. Not the beginning of the universe, but the beginning of Betelgeuse itself. Roughly 8 to 10 million years ago, somewhere in the Orion region of our galaxy, a cloud of gas and dust began to collapse. This is how all stars are born. Maybe a nearby supernova sent a shockwave through the cloud. Maybe the cloud simply reached a critical density on its own. Either way, gravity took over. The cloud began to contract, pulling material inward. As the material fell inward, it heated up. The center of the collapsing cloud grew hotter and denser. Eventually, the temperature and pressure at the core became so extreme that hydrogen atoms began to fuse together, forming helium. Nuclear fusion ignited. A star was born. But this newborn star looked nothing like the Betelgeuse you see today. When Betelgeuse first ignited, it was a hot, brilliant, blue-white star. It was what astronomers call an O-type or B-type main sequence star. One of the most luminous and hottest categories of stars that exist. Its surface temperature would have been somewhere around 25,000 to 30,000 degrees, compared to the sun's surface temperature of about 5,500 degrees. It would have blazed with a fierce blue-white light, far more intense than anything the sun produces. If you had been alive 8 million years ago and looked up at the sky from Earth, assuming Betelgeuse was close enough to see, you would not have recognized it as the same star. It would have been a searing blue point of light, not the reddish-orange glow you see today. This is the first crucial point. The Betelgeuse you see tonight is not what Betelgeuse has always been. The red supergiant phase is a late stage of evolution. It's the stellar equivalent of old age, though in Betelgeuse's case, old age arrived remarkably fast. And the reason it arrived so fast brings us to the most important relationship in all of stellar physics. The relationship between a star's mass and its lifespan. Here is the central truth that governs the life of every star in the universe. The more massive a star is, the shorter it lives. This might seem counterintuitive at first. You might think that a star with more mass has more fuel, so it should last longer. And it's true that a more massive star does have more hydrogen to burn. But here's the catch. It doesn't just burn that fuel a little faster, it burns it enormously faster. The rate at which a star consumes its nuclear fuel doesn't scale linearly with mass. It scales as roughly the third or even fourth power of the mass. This means that if you double a star's mass, you don't double its fuel consumption rate. You increase it by a factor of 8 to 16. If you multiply a star's mass by 10, you multiply its fuel consumption rate by roughly 1,000 to 10,000. Let's see what this means in practice. The sun has been burning hydrogen in its core for about 4.5 billion years. It is enough fuel to keep going for roughly another 5 billion years. That gives the sun a total main sequence lifespan of about 10 billion years. 10 billion years of steady, stable hydrogen fusion. The sun was burning before complex life existed on Earth. It was burning before the dinosaurs. It was burning before the continents we recognize today had even formed, and it will keep burning for billions of years after we're gone. Now, consider a star with 10 times the mass of the Sun. You might expect it to live about 1/10 as long, since it has 10 times the fuel, but is burning it faster. But the fuel consumption rate doesn't just multiply by 10, it multiplies by something closer to 1,000 or more. So a star with 10 times the Sun's mass doesn't live for 1 billion years. It lives for roughly 20 to 30 million years. That's a dramatic difference. The Sun lives for 10 billion years. A star 10 times more massive lives for perhaps 20 million years. The massive star has 10 times the fuel, but it's burning through that fuel at a rate roughly 3,000 times higher. It's like comparing a candle to a bonfire. The bonfire has more wax, yes, but it's consuming that wax at such a ferocious rate that it burns out almost immediately by comparison. Betelgeuse is estimated to have a mass of about 15 to 20 times the Sun. At that mass, its total lifespan from birth to death is roughly 8 to 10 million years. That's it. 8 to 10 million years for an entire stellar lifetime. Compare that to the Sun's 10 billion years. Betelgeuse will live and die in roughly 1,000th the time the Sun will live. If the Sun's life were a single calendar year, Betelgeuse's entire existence would be compressed into about 8 hours. Born in the morning, dead before midnight. And here's the thing that really drives this home. Betelgeuse is already near the end of those 8 to 10 million years. It has already left the main sequence. It has already exhausted the hydrogen in its core. It has already expanded into its current red supergiant state. Most of its life is behind it. The clock is running out. Why does mass cause such extreme fuel consumption? The answer lies in what's happening at the core of a massive star. The core of a star is where nuclear fusion occurs. Gravity is constantly trying to crush the star inward. The only thing preventing the star from collapsing under its own weight is the outward pressure generated by nuclear fusion. The more massive the star, the stronger gravity pulls inward, which means the core has to burn hotter and faster to generate enough outward pressure to resist collapse. A more massive star needs more energy output to hold itself up, and more energy output means faster fuel consumption. The core temperature of a star like the Sun is about 15 million degrees. At this temperature, hydrogen fuses through a process called the PP chain, which is relatively slow and efficient. The Sun converts its hydrogen into helium at a measured, sustainable pace. But in a star like Betelgeuse, the core temperature during main sequence hydrogen burning would have been much higher, perhaps 40 million degrees or more. At these temperatures, hydrogen fusion occurs primarily through a different process called the CNO cycle, which is far more temperature sensitive. A small increase in temperature produces a dramatically larger increase in fusion rate. The result is that massive stars don't just burn a little faster. They burn furiously. They pour out energy at rates that dwarf what smaller stars produce. During its main sequence life, Betelgeuse would have been roughly 10,000 to 30,000 times more luminous than the Sun. That might sound modest compared to its current output of roughly 100,000 solar luminosities, but it was already vastly more energy than the Sun produces. That furious output is what burned through its fuel in mere millions of years instead of billions. And as Betelgeuse evolved off the main sequence and expanded into its current red supergiant state, its luminosity climbed even higher, making its fuel crisis even more severe. Now here's where the story takes a dramatic turn. What happens when a star exhausts the hydrogen in its core? For a star like the Sun, this is an event that won't happen for another 5 billion years. But for Betelgeuse, it already happened millions of years ago, and the consequences were immediate and dramatic. When the hydrogen in the core is used up, the core is left as a ball of helium. Helium is the ash of hydrogen fusion, the waste product. And for a brief moment, fusion in the core stops. Without fusion generating outward pressure, gravity begins to win. The core starts to contract. As it contracts, it heats up. This is a basic principle of physics. When you compress a gas, it gets hotter. The core contracts and heats, getting denser and hotter with each passing moment. Meanwhile, something interesting happens in the layers just above the core. There's still hydrogen there. Hydrogen that was never hot enough or under enough pressure to fuse while the core was active. But now, as the core contracts and heats up, the layer of hydrogen just outside the core, the hydrogen shell, gets heated to fusion temperatures. Hydrogen fusion ignites in a shell around the dead helium core. This is called shell burning, and it changes the star's structure dramatically. Shell burning produces an enormous amount of energy. In fact, the energy output from shell burning is greater than what the core was producing when it was actively fusing hydrogen. This flood of energy pushes the outer layers of the star outward. The star begins to expand. And it doesn't expand a little. It expands enormously. The outer layers push outward and outward, cooling as they go because the same amount of energy is now spread across a much larger surface area. The surface temperature drops. The star changes color. What was once a blue-white furnace becomes a cooler, redder, vastly larger object. A red giant is born. Or in the case of a star as massive as Betelgeuse, a red supergiant. This is exactly what happened to Betelgeuse. Millions of years ago, its core ran out of hydrogen. The core contracted. A hydrogen-burning shell ignited around the core. The outer layers expanded to the monstrous dimensions we see today. The blue-white star became a red supergiant, bloated and enormous, its surface now relatively cool at only about 3,400 degrees, compared to the roughly 30,000 degrees it had during its youth. The color shifted from brilliant blue to deep red. The size increased by a factor of hundreds. And all of this happened because the star ran out of hydrogen in its core. But the story doesn't stop with hydrogen shell burning. Because the core, that ball of helium, is still contracting under gravity's relentless pull. And as it contracts, it keeps getting hotter. Eventually, the core reaches a temperature of about 100 million degrees. At this temperature, something new happens. Helium itself begins to fuse. 3 helium nuclei combine to form a carbon nucleus in a process called the triple alpha process. Helium becomes fuel. The core ignites again, now burning helium instead of hydrogen. This is a crucial moment, but it's also a brief one by stellar standards. Helium fusion releases less energy per reaction than hydrogen fusion, and the star needs more energy than ever to support its now enormous structure. The result is that helium burning happens much faster than hydrogen burning. While hydrogen burning in Betelgeuse's core lasted millions of years, helium burning lasts roughly 1 million years. Maybe a bit more, maybe a bit less, but dramatically shorter than the hydrogen phase. When the helium in the core is exhausted, you're left with a core of carbon and oxygen, and the process repeats. The core contracts, heats up, and eventually reaches the temperature needed to ignite the next fuel. carbon begins to fuse. Carbon fusion requires a core temperature of roughly 600 million degrees. At these extreme temperatures, carbon nuclei smash together and produce neon, sodium, and magnesium. Carbon burning is even faster than helium burning. In a star like Betelgeuse, the carbon burning phase lasts roughly 1,000 years. 1,000 years, compare that to the millions of years of hydrogen burning. The star is accelerating toward its end. After carbon is exhausted, the core contracts further and heats to about 1.5 billion degrees. Neon burning begins. Neon fuses into oxygen and magnesium. This phase lasts only about 1 year, a single year. After neon comes oxygen burning. The core reaches about 2 billion degrees. Oxygen nuclei fuse together to produce silicon, sulfur, and other elements. Oxygen burning lasts perhaps 6 months to a year, and then comes the final stage of nuclear burning. Silicon fusion. The core reaches about 3 billion degrees, and silicon nuclei begin to fuse. The product of silicon fusion is iron. And silicon burning, the last phase of nuclear fusion in a massive star's life, lasts roughly 1 day. 1 single day. Let me lay this out as a timeline so the acceleration becomes impossible to ignore. Hydrogen burning, the main sequence phase, lasts about 8 million years. Helium burning lasts about 1 million years. Carbon burning lasts about 1,000 years. Neon burning lasts about 1 year. Oxygen burning lasts about 6 months to a year. Silicon burning lasts about 1 day. Do you see the pattern? Each phase is dramatically shorter than the one before it. The star is racing through its fuel reserves at an accelerating pace. It's like watching someone sprint toward a cliff, getting faster with every step. This acceleration happens for 2 reasons. First, each successive fusion reaction produces less energy per reaction than the previous one. Hydrogen fusion is the most efficient, helium fusion is less efficient, carbon fusion even less. By the time you get to silicon, the energy payoff per reaction is tiny compared to hydrogen. The star has to burn through its fuel faster and faster just to generate enough energy to hold itself up against gravity. Second, the temperatures required for each successive reaction are higher. Higher temperatures mean more energy is lost through neutrino emission. Neutrinos are ghostly particles that barely interact with matter. They pass right through the star and escape into space, carrying away energy that the star desperately needs. At the temperatures required for carbon, neon, oxygen, and silicon burning, neutrino losses become enormous. The star is leaking energy through neutrino emission at a staggering rate, which forces it to burn its fuel even faster to compensate. The result is that the final stages of a massive star's life happen at a dizzying pace. A star that burned hydrogen steadily for millions of years tears through its remaining fuel reserves in centuries, then years, then months, then days. The end, when it comes, arrives shockingly fast. And this is where the structure of the star becomes particularly fascinating. As each fuel is exhausted in the core and the next one ignites, the previous fuel doesn't disappear from the star. It continues to burn in shells around the core. So the star develops a layered structure like the layers of an onion. At the very center sits the core, which is burning whatever the current fuel is. Around the core is a shell burning the previous fuel. Around that shell is another shell burning the fuel before that. And so on, all the way out to the surface. In the final stages of Betelgeuse's life, the star's interior will look something like this. At the very center, an iron core. The ash of silicon burning, no longer capable of fusion. Surrounding that, a thin shell burning silicon into iron. Around that, a shell burning oxygen into silicon. Then a shell burning neon into oxygen. Then a shell burning carbon into neon. Then a shell burning helium into carbon. And finally, far out near the surface, a shell burning hydrogen into helium. Each shell is nested inside the next, like concentric spheres, each one burning a different fuel, each one producing different elements. This layered onion structure is one of the most remarkable things about a dying supergiant. The star becomes a factory for building heavy elements. Hydrogen and helium at the top, carbon and oxygen deeper down, neon, magnesium, silicon, sulfur, and finally iron at the very core. All the elements that make up rocky planets, that make up the metals in our buildings, the calcium in our bones, the iron in our blood. These elements are being forged right now inside stars like Betelgeuse. Not all at once, but layer by layer, shell by shell, in this incredible nested structure that only exists in the final stages of a massive star's life. But here is the critical detail. Iron is different from every element that came before it. Every previous fusion reaction, from hydrogen to helium, from helium to carbon, from carbon to neon, all the way through the chain, every one of those reactions released energy. That released energy is what kept the star alive. It generated the outward pressure that resisted gravity. But iron does not release energy when it fuses. Iron is the most tightly bound nucleus. It sits at the bottom of the nuclear binding energy curve. To fuse iron into heavier elements requires energy. It doesn't release energy, it consumes it. This means that when the core of a massive star fills it with iron, fusion can no longer help the star. There is no next fuel. There is no next stage of burning that will generate energy and hold the star up. The iron core just sits there, growing heavier and heavier as the silicon burning shell above it dumps more iron onto it. Gravity is pulling it inward. And for the first time in the star's life, there is nothing to push back. This is the point of no return. This is the moment the star has been racing toward since the day it was born. Every phase of its life, every fuel it burned, every expansion and contraction, all of it was leading here. To an iron core that cannot burn. To a star that has run out of options. What happens next will be the most violent event this star will ever experience. In fact, it will be one of the most violent events in the entire universe, and it will happen not over millions of years or thousands of years, but in seconds. We are now standing at the edge of the story. We understand why Betelgeuse is so large. We understand that its size is not a sign of strength, but a sign that its core has already exhausted its primary fuel and moved on to increasingly desperate alternatives. We understand that each successive fuel burns faster than the last, accelerating the star toward an inescapable endpoint. And we understand that that endpoint is iron, the element that kills stars. The question now is what happens when that iron core reaches its limit? What happens when gravity finally wins the battle it has been fighting since the star was born? The answer is a supernova. And the physics of how a supernova works, how a star that took millions of years to build destroys itself in seconds, is one of the most dramatic stories in all of science. Betelgeuse's enormous size, its restless pulsations, its shedding of material into space, all of these are symptoms of a star that is deep into the final chapters of its existence. The clock that started ticking 8 to 10 million years ago is winding down. The fuel is running out. The iron core is growing, and when it reaches its limit, The star that swallowed planets will tear itself apart in an explosion brighter than billions of suns. We've now traced the life of Betelgeuse, from its birth as a blazing blue-white star to its current state as a bloated red supergiant, swollen to dimensions so enormous that it would swallow the inner planets of our solar system. And we've arrived at the critical moment. The core of the star is filling up with iron. The last fuel, silicon, is being consumed in a shell around that iron core, and every reaction dumps more iron into the center. But iron is the element that cannot fuse to release energy. It is the dead end of nuclear fusion. The road that began with hydrogen and passed through helium, carbon, neon, oxygen, and silicon terminates here. There is no next step. There is no escape. And what happens next unfolds not over millions of years, not over thousands of years, not even over days. It unfolds in seconds, literal seconds. The death of a supergiant star is one of the fastest and most violent processes in the known universe, and it begins with the quiet, invisible accumulation of iron at the star's heart. Let's go inside the star, deep inside, past the enormous bloated outer layers that stretch across hundreds of millions of miles, past the nested shells of burning fuel, each one smaller and hotter than the one above it, all the way down to the core. The core at this stage is roughly the size of Earth, perhaps a bit larger. It's incredibly dense, far denser than anything you've ever encountered. A teaspoon of material from this iron core would weigh roughly 5 to 50 tons on Earth's surface, depending on how close to the center you sampled. The temperature is around 3 billion degrees. The pressure is beyond anything that exists anywhere else in the universe outside of other dying stellar cores and neutron stars. And yet, despite this extreme density and temperature, the core is holding itself up. Not through nuclear fusion, because iron can't fuse to produce energy, but through something else entirely. The core is supported by a quantum mechanical effect called electron degeneracy pressure. Electron degeneracy pressure is one of the most counterintuitive concepts in physics, but it's essential for understanding what happens next. In normal matter, atoms have electrons orbiting their nuclei in various energy levels. Under extreme compression, atoms are stripped of their electrons. The matter becomes a dense soup of free electrons and atomic nuclei. When this electron soup is compressed to extreme densities, a fundamental rule of quantum mechanics kicks in: the Pauli exclusion principle. This principle states that no two electrons can occupy the same quantum state. As the electrons are squeezed closer and closer together, they resist further compression because they literally cannot be pushed into the same state. This resistance creates an outward pressure, electron degeneracy pressure, that doesn't depend on temperature, it depends only on density. Even if the core were completely cold, this pressure would still exist. For a while, electron degeneracy pressure holds the iron core up. Gravity is pulling inward. Electron degeneracy pressure is pushing outward. There's a tense standoff, but here's the critical point. There is a limit to how much mass electron degeneracy pressure can support. This limit was calculated in 1930 by a brilliant young Indian astrophysicist named Subramanian Chandra Sekhar. He was only 19 years old at the time, working out the mathematics on a steamship voyage from India to England. What he discovered was that if the mass of a stellar core exceeds roughly 1.4 times the mass of the Sun, electron degeneracy pressure cannot hold it up. No matter how much the electrons resist, gravity wins. This mass limit is called the Chandra Sekhar limit, and it is one of the most important numbers in all of astrophysics. In a star like Betelgeuse, the iron core is growing. Silicon burning in the shell above is constantly adding more iron to the core. The core's mass creeps upward, approaching the Chandrasekhar limit. And then, in a matter of moments, the core crosses the threshold. The mass exceeds 1.4 solar masses. Electron degeneracy pressure can no longer support the core against gravity, and the core collapses. The collapse is almost instantaneous. The core, which is roughly the size of Earth at this point, about 8,000 miles across, collapses in on itself. The material falls inward at speeds reaching about 70,000 kilometers per second. That is nearly a quarter of the speed of light. In less than 1 second, the core that was the size of Earth collapses down to a sphere roughly 12 miles across. 12 miles, the size of a small city. All the mass of the core, roughly 1.5 times the mass of the Sun, is compressed into a ball 12 miles in diameter. Let me make sure you understand the scale of what just happened. In less than 1 second, an object the size of Earth collapsed into something the size of a city. The density of this collapsed object is beyond comprehension. A teaspoon of material from the collapsed core would weigh about 4 billion tons. That single teaspoon, a volume smaller than a marble, would weigh more than every ship ever built by humanity combined. This is nuclear density. The protons and electrons in the core have been squeezed together so tightly that they merge, forming neutrons. What was once an iron core made of atoms is now a ball of neutrons packed together like marbles in a jar. This object is a proto-neutron star, and it will become the remnant left behind after the explosion. But what stops the collapse? If electron degeneracy pressure failed, what prevents the core from collapsing all the way to a point, all the way to a black hole? The answer is another form of degeneracy pressure, this time involving neutrons. Neutron degeneracy pressure, governed by the same Pauli exclusion principle, but applied to the neutrons instead of electrons, resists further compression. Neutrons, like electrons, cannot occupy the same quantum state. When they're packed together at nuclear density, they push back. The collapse slams to a halt, and this is where the explosion begins. The infalling material from the outer layers of the core is still plunging inward at a significant fraction of the speed of light. It slams into the newly formed neutron star, which has suddenly become incredibly rigid. Think of it like dropping a rubber ball onto a concrete floor. The ball hits the floor and bounces. The infalling material hits the surface of the neutron star and bounces. This bounce sends a powerful shockwave outward through the star. This shockwave is immensely energetic. It tears outward through the layers of the star at thousands of kilometers per second. But here's the problem. The shockwave has to fight its way through an enormous amount of material. Remember, Betelgeuse has roughly 15 to 20 times the mass of the Sun, and most of that mass is in the outer layers above the core. The shockwave has to push through all of it, and as it does, it loses energy. It slows down. Within milliseconds, the shockwave stalls. It doesn't have enough energy to blow the star apart on its own. This is where the physics gets truly extraordinary. For decades, astrophysicists struggled to understand how supernovae actually work because of this stalling problem. The bounce alone doesn't produce enough energy to unbind the star. Something else has to provide the extra push, and that something turns out to be neutrinos. During the core collapse, the merger of protons and electrons into neutrons produces an almost unimaginable flood of neutrinos. Neutrinos are subatomic particles that barely interact with normal matter. Under ordinary circumstances, a neutrino could pass through a wall of lead a light year thick without hitting anything. They're ghostly, nearly massless, almost impossible to detect. But during a core collapse supernova, the conditions are anything but ordinary. The number of neutrinos produced during the collapse is staggering. In about 10 seconds, the collapsing core releases roughly 10 to the 58 neutrinos. That's a 1 followed by 58 zeros. The total energy carried by these neutrinos is approximately 3 times 10 to the 46 joules. To put that in perspective, the Sun produces about 3.8 times 10 to the 26 joules of energy per second. The neutrino burst from a core collapse supernova carries more energy in 10 seconds than the Sun will produce in its entire 10 billion year lifetime. In fact, the neutrino energy output is roughly 250 times greater than the total energy the Sun will ever produce. This is the true power source of a supernova, not the bounce, not the shockwave, neutrinos. Now, neutrinos barely interact with matter. Under normal conditions, nearly all of them would simply fly straight out of the star without doing anything. And in fact, that's mostly what happens. The vast majority of neutrinos escape the star entirely, carrying their energy away into space. Roughly 99% of the supernova's total energy output is in the form of these escaping neutrinos, rather than light or kinetic force. But the conditions at the edge of the stalled shockwave are not normal. The densities are so extreme, so far beyond anything in ordinary experience, that even neutrinos, particles that can pass through light years of solid LED, start to interact. A small fraction of the neutrino flood, perhaps 5 to 10%, deposits its energy into the material just behind the stalled shockwave. And that small fraction of an enormous total is enough. The deposited energy revives the shockwave. It pushes it outward again with renewed force. The shockwave accelerates, tearing through the outer layers of the star, ripping the star apart from the inside out. The star explodes. This is a core collapse supernova. Specifically for a star like Betelgeuse, it will be classified as a Type 2 supernova. The explosion is almost beyond description. The total energy released in those first 10 seconds, overwhelmingly carried by neutrinos, is roughly 250 times greater than everything the Sun will produce across its entire 10 billion year lifetime. Most of that energy is invisible, carried away by neutrinos that pass straight through the star and escape into space. But roughly 1% of the total energy goes into the kinetic energy of the explosion itself, the actual physical blast that tears the star apart, and about 0.1% goes into light, electromagnetic radiation visible across the cosmos. Even that tiny fraction of the total energy, 0.1%, produces a light show that is staggering. At peak brightness, a supernova can outshine its entire host galaxy. A single exploding star producing more visible light than 100 billion stars combined. For a few weeks, this one dying star is brighter than everything else in the galaxy put together. The outer layers of the star, the hydrogen envelope, the helium shell, all the layered shells of carbon, neon, oxygen, and silicon, everything above the core is blasted outward into space at speeds of roughly 10,000 to 30,000 kilometers per second. That's 3 to 10% of the speed of light. Material that was part of a star moments ago is now a rapidly expanding cloud of gas and debris, glowing intensely from the heat of the explosion laced with every element the star forged during its life, and new elements created in the explosion itself. This is something important. The extreme temperatures and pressures of the supernova explosion create conditions that allow the formation of elements heavier than iron. Remember, iron is the endpoint of energy-releasing fusion. You can't get past iron by ordinary stellar burning. But during a supernova, there's so much energy available that neutrons are captured by atomic nuclei at a furious rate, building up heavier and heavier elements. Gold, platinum, uranium. All the elements heavier than iron on the periodic table are forged in supernova explosions or similar cataclysmic events. The gold in a wedding ring was made in a supernova. The uranium that powers nuclear reactors was made in a supernova. These elements do not exist in the universe without the violent deaths of massive stars. Every atom of these heavy elements in your body, in the earth, in everything around you, was produced in an event exactly like the one Betelgeuse will eventually experience. After the explosion, what remains at the center? The neutron star. That tiny ball of neutrons, 12 miles across, containing roughly 1.5 to 2 times the mass of the Sun, spinning rapidly, often many times per second, with an incredibly powerful magnetic field. Neutron stars are among the most extreme objects in the universe. Their surface gravity is about 200 billion times stronger than Earth's. If you dropped an object from a height of 1 meter above a neutron star's surface, it would hit the surface traveling at about 2 million meters per second. The escape velocity from a neutron star's surface is roughly half the speed of light or more. These are objects so dense that a sugar cube-sized piece of them would weigh as much as all of humanity combined. That single hotspot spanned roughly 1/5 of the stellar disk, stretching well over 100 million miles across. A single bright patch on the face of a star, wider than the entire distance from Earth to the Sun. Some neutron stars emit beams of radiation from their magnetic poles. As the neutron star spins, these beams sweep across space like lighthouse beams. If one of these beams happens to point toward Earth, we detect regular pulses of radiation. We call these objects pulsars. The first pulsar was discovered in 1967 by Jocelyn Bell Burnell and Anthony Hewish. The signal was so regular, so precise, that the discoverers briefly considered the possibility it might be an artificial signal from an extraterrestrial civilization. They nicknamed the source LGM1 for Little Green Men 1. It turned out to be a rapidly spinning neutron star, but the precision of its pulses was genuine. Pulsars are among the most accurate clocks in the universe, rivaling atomic clocks in their regularity. There is another possibility for Betelgeuse's remnant. If the core mass after the explosion exceeds roughly 2 to 2.5 times the mass of the Sun, even neutron degeneracy pressure cannot hold it up. The core collapses past the neutron star stage and becomes a black hole. Whether Betelgeuse will leave behind a neutron star or a black hole depends on exactly how much mass falls back onto the core during and after the explosion. This is one of the uncertainties in supernova physics. The initial mass of the core, the details of the explosion, how much material is ejected versus how much falls back, all of these affect the final outcome. Most models suggest that Betelgeuse's core will likely produce a neutron star rather than a black hole, but a black hole outcome cannot be entirely ruled out. The dividing line between neutron star and black hole is thin, and Betelgeuse sits in a mass range where the outcome is not completely certain. Now, you might be wondering whether this picture of a supernova is theoretical or whether we've actually observed one. The answer is that we've observed many. Astronomers have detected thousands of supernovae in other galaxies. But the most important observation for confirming our understanding of core collapse, supernovae, came on February 23rd, 1987. On that date, a star exploded in the Large Magellanic Cloud, a small satellite galaxy of the Milky Way, about 168,000 light-years from Earth. The supernova was designated Supernova 1987A, and it was the closest observed supernova since the invention of the telescope. The star that exploded was a blue supergiant called Sandu Li-Ak -69 degrees 202. It had a mass of roughly 20 times the Sun, similar to what Betelgeuse is estimated to have, and it died in exactly the way our models predicted. But the most remarkable confirmation came not from light, but from neutrinos. About 3 hours before the visible light from the explosion reached Earth, 3 neutrino detectors registered a sudden burst of neutrinos. Kamiokande 2 in Japan detected 12 neutrinos in a span of about 13 seconds. The IMB detector in the United States detected 8 neutrinos in about 6 seconds, and the Baksan detector in Russia detected 5 more in about 9 seconds. That might not sound like much, but remember, neutrinos barely interact with matter. The fact that even a handful were detected from a supernova 168,000 light-years away, after passing through the entire star and crossing a gulf of space spanning nearly 1,000,000 trillion miles, confirms that the neutrino burst from a supernova is exactly as enormous as our models predict. Those 25 neutrinos represented a tiny, almost infinitesimal fraction of the total neutrino flood. The vast majority, the overwhelming bulk of 10 to the 58 neutrinos, pass through both detectors and through the entire Earth without interacting at all. They flew straight through our planet as though it weren't there. Supernova 1987A was a watershed moment in astrophysics. It confirmed that our theoretical understanding of core collapse supernovae is fundamentally correct. The iron core reaches the Chandrasekhar limit. Electron degeneracy pressure fails. The core collapses. A neutron star forms. A shockwave is launched. Neutrinos provide the energy to revive the stalled shock. The star explodes. The sequence we've described isn't speculation. It's confirmed physics, tested against real observations. The remnant of supernova 1987A has been studied extensively in the decades since the explosion. The expanding debris cloud is visible through telescopes, glowing as it collides with gas the star shed before exploding. At the center, astronomers have long searched for the neutron star that should have been left behind. For decades, the debris was too thick and too bright to see through. But in recent years, evidence has emerged strongly suggesting that a neutron star is indeed sitting at the center, exactly where our models say it should be. It took nearly 4 decades of improving telescope technology to glimpse it, but the remnant appears to be there, quietly spinning in the wreckage of the star that created it. Let's take a moment to appreciate the energy scales involved, because they truly defy ordinary comprehension. A core collapse supernova releases roughly 3 times 10 to the 46 joules of total energy, mostly in neutrinos. The kinetic energy of the ejected material is about 10 to the 44 joules. The radiated light energy is about 10 to the 43 joules. The sun's total luminosity is about 3.8 times 10 to the 26 joules per second. Over its entire 10 billion year main sequence lifetime, The sun will produce roughly 10 to the 44 joules of energy in the form of light. A supernova produces that much energy in kinetic force alone, and the kinetic energy is only about 1% of the total. The remaining 99%, carried away by neutrinos, dwarfs the kinetic blast by a further factor of 100. Virtually all of that neutrino energy is released in a burst lasting roughly 10 seconds. The brevity is staggering. 10 seconds of output exceeding everything the sun will ever produce across its entire existence. The visible light output, while only a fraction of the total, is still extraordinary. At peak brightness, a supernova can outshine its entire host galaxy. A single dying star briefly producing more visible light than 100 billion stars combined. The sheer energy released in those first moments dwarfs anything else a star will ever do in its entire existence. And because Betelgeuse is relatively close to us in cosmic terms, a mere 550 light-years away, its supernova would be one of the most dramatic celestial events in recorded human history. We'll explore exactly what that would look like from Earth shortly. But first, we need to understand what is left behind after the explosion. And after the light fades, after the initial brilliance dims over weeks and months, what remains is an expanding cloud of debris, a supernova remnant, carrying with it all the elements the star forged during its lifetime. Hydrogen and helium from the outer layers, carbon, oxygen, neon, magnesium, silicon, sulfur, and iron from the inner shells, and all the heavier elements produced in the explosion itself. This debris spreads outward into interstellar space at thousands of kilometers per second. Over thousands of years, it expands and cools, mixing with the surrounding gas and dust of the interstellar medium. And here is where the story comes full circle. That enriched gas, laden with heavy elements from the dead star, eventually becomes part of new molecular clouds. Those clouds will one day collapse under their own gravity, forming new stars and new planets. The heavy elements from the supernova, the carbon, the oxygen, the iron, the gold, will be incorporated into those new worlds. Some of those planets might develop oceans, some might develop atmospheres, some might develop life. This is not poetry. This is physics. The atoms in your body were forged in the cores of massive stars that lived and died billions of years ago. The iron in your blood was made by silicon fusion in the core of a star that exploded before our sun was born. The oxygen you breathe was made by nuclear burning in a supergiant that no longer exists. You are, quite literally, made of the remains of dead stars. And Betelgeuse, the red supergiant glowing softly in Orion's shoulder tonight, will one day contribute its own elements to this cycle. Its carbon, its oxygen, its silicon, its iron, and all the heavier elements forged in its supernova will be scattered across space, eventually becoming part of new stars, new planets, and perhaps new life. The death of a massive star is not just an ending, it is the beginning of everything that comes after. Without supernovae, there would be no rocky planets, no liquid water, no complex chemistry, no life as we know it. The violence of a supernova is not wasteful destruction. It is the universe's mechanism for distributing the building blocks of complexity across space. Every supernova seeds the galaxy with the raw materials for the next generation of stars and worlds. Betelgeuse will die this way. Not gently, not slowly, not with a whimper. It will die in an explosion so powerful that for a few brief weeks, a single star will outshine billions. Its core will collapse in less than a second. A flood of neutrinos will carry more energy than the sun will ever produce. Its outer layers will be blasted into space at a significant fraction of the speed of light. And what remains at the center will be either a neutron star, an object so dense that a teaspoon of it weighs billions of tons, or possibly a black hole, a region of space-time so warped that nothing, not even light, can escape. This is the fate that awaits every red supergiant. Every star massive enough to build an iron core will end this way. It is not a question of if, it is only a question of when. The physics is settled. The process is understood. We have observed it happen in other galaxies and confirmed our predictions with neutrino detectors and telescopes. The only remaining question for Betelgeuse is timing. And that question, the question of when, is what we need to address next. We now understand what Betelgeuse is. We understand its staggering size. We understand how its enormous mass drove it through its fuel at an accelerating pace, each stage shorter than the last, from millions of years of hydrogen burning down to a single day of silicon fusion. We understand the layered onion structure developing inside it right now. Shells of different elements burning in concentric rings around an ever-growing core. And we understand what happens at the end. The iron core exceeds the Chandrasekhar limit. Electron degeneracy pressure fails. The core collapses in less than a second. A flood of neutrinos revives a stalled shockwave. The star tears itself apart in one of the most violent events the universe can produce. The physics is settled. The outcome is certain. Betelgeuse will explode as a core collapse supernova. There is no alternative ending, no path that leads to a quiet retirement. For a star this massive, the only possible death is a violent one. So the question everyone asks is obvious: when? And the honest answer, the scientifically rigorous answer, is that we don't know precisely. We know it will happen. We know the mechanism. We can describe the explosion in extraordinary detail. But pinpointing exactly when the core will cross its fatal threshold is beyond our current ability. Estimates place the supernova somewhere within the next 100,000 years, and possibly much sooner. But 100,000 years is a wide window. To a human being, 100,000 years might as well be forever. To a star, it's the blink of an eye. Betelgeuse has already lived for roughly 8 to 10 million years. 100,000 years is about 1% of its total life. In human terms, if Betelgeuse's life were 80 years, the remaining uncertainty would be like saying someone in their final year of life will die within the next 3 days, but you can't say which day. The difficulty in predicting the exact timing comes from the fact that we cannot see inside the star. We can measure its brightness, its temperature, its size, its chemical composition from spectral lines. But the crucial action is happening deep inside, at the core, buried beneath hundreds of millions of miles of stellar material. We don't know if the core is still fusing helium, or if it has moved on to carbon or neon, or something further along the chain. Each of those stages has a different duration. If the core is still burning helium, Betelgeuse might have hundreds of thousands of years left. If it's already burning carbon, the timeline shrinks to roughly 1,000 years. If it's burning neon or oxygen, we're talking about years. And if it's burning silicon, the star has less than a day. Some recent studies, particularly work published in the early 2020s, have attempted to narrow this window. Several research groups analyzed Betelgeuse's pulsation behavior and luminosity, and suggested it may be further along in its evolution than previously thought, potentially already in the carbon-burning phase. If that is correct, then the supernova could occur within the next few thousand years, rather than the next 100,000. But these conclusions remain debated within the astronomical community. Different models produce different answers depending on the assumptions used. The mass of the star, which is itself uncertain, has a huge effect on the calculations. A star of 15 solar masses evolves differently from one of 20 solar masses, and Betelgeuse's mass is not known to better than a rough range. The distance to Betelgeuse also matters because distance affects how we calculate the star's luminosity, and luminosity is one of the key inputs for determining where the star is in its evolutionary sequence. For centuries, Betelgeuse has been known as a variable star. Its brightness changes over time, sometimes noticeably. This variability has multiple overlapping cycles. The most prominent has a period of roughly 400 days. There are longer cycles of roughly 2,000 days, and possibly even longer ones stretching over decades. These pulsations are caused by physical changes in the star itself. The outer layers expand and contract, heating and cooling, causing the brightness to rise and fall. This kind of behavior is common in red supergiants. They are inherently unstable objects, their enormous distended envelopes sloshing and heaving as convective currents churn material from deep inside the star up to the surface and back down again. But in late 2019 and early 2020, Betelgeuse did something that captured worldwide attention. It dimmed, not by a subtle amount that only astronomers would notice. It dimmed dramatically, its brightness falling to roughly 36% of its normal level, dropping it from one of the 10 brightest stars in the sky to something that barely stood out in Orion. For a star that is usually one of the 10 brightest in the entire sky, this was extraordinary. Betelgeuse became visibly fainter to the naked eye. The constellation Orion looked noticeably different. Betelgeuse, which normally dominates Orion's shoulder with its bright reddish glow, became dim and subdued, almost fading into the background. The event was quickly dubbed the Great Dimming, and it triggered an enormous amount of public speculation. Headlines asked whether Betelgeuse was about to explode. Social media buzzed with excitement and anxiety. People who had never thought twice about the star suddenly wanted to know if a supernova was imminent. The idea that a visible star might explode in their lifetime was electrifying. For a few months, Betelgeuse was one of the most talked about objects in all of science. But here's what actually happened. And it's important because it illustrates the difference between what is exciting and what is scientifically accurate. Betelgeuse did not dim because it was about to explode. The Great Dimming had nothing to do with the star's core or its progression towards supernova. Detailed observations, particularly from the European Southern Observatory's VLT in Chile, and later confirmed by multiple research teams, revealed that the dimming was caused by two factors working together. First, Betelgeuse experienced a massive ejection of material from its surface. A huge blob of hot gas was expelled outward from the star. This is not unusual for red supergiants. As we discussed earlier, Betelgeuse has been shedding material for millennia, its enormous convective plumes constantly flinging gas outward into space. But this particular ejection was larger than normal. Second, as the ejected material moved away from the star and cooled, it condensed into dust. Tiny grains of solid material formed in the expelled gas cloud. This dust cloud drifted in front of the star from our line of sight, partially blocking Betelgeuse's light. The dimming wasn't the star becoming intrinsically fainter. It was the star being obscured by a cloud of his own dust. Imagine standing in front of a bright lamp and then blowing a handful of fine powder into the air between you and the lamp. The lamp looks dimmer, but it hasn't changed. Something is just blocking part of its light. That's essentially what happened with Betelgeuse. By early 2020, the dust cloud had dispersed enough that Betelgeuse began to brighten again. Within several months, it had returned to its normal brightness range. The event was fascinating from a scientific perspective because it gave astronomers a close-up look at how red supergiants shed mass and form dust in real time. It advanced our understanding of the processes occurring in Betelgeuse's outer atmosphere. But it told us nothing about when the star will explode. The Great Dimming was a surface event, not a core event. The supernova will be triggered by what happens at the center of the star, and the surface events we observe, while interesting, are not reliable indicators of the core's status. This is a crucial distinction that often gets lost in popular coverage. Betelgeuse's variability, its dimming events, its pulsations, none of these are signs that the supernova is imminent. Red supergiants pulsate and shed mass as a normal part of their existence. They've been doing it for hundreds of thousands of years and will continue doing it until the core finally collapses. A dramatic dimming event might happen 100,000 years before the supernova, or it might happen a week before. There's no established connection between surface variability and the timing of core collapse. The core and the surface are so far apart, separated by hundreds of millions of miles of stellar material, that events at the core take a very long time to manifest at the surface, if they ever do in a detectable way. So what would we actually see if Betelgeuse's core were about to collapse? This is a question astronomers have thought about carefully. The honest answer is that there might be very little warning. The final stages of nuclear burning happen so fast that the surface of the star may not have time to respond in any visible way. Silicon burning, the last stage before core collapse, lasts about a day. That's far too short for any signal to propagate from the core to the surface of a star this large. Light itself would take hours to cross the interior of Betelgeuse, and any structural changes would propagate even more slowly. The star's surface might look completely normal right up until the moment the supernova begins. The first detectable signal would not be light. It would be neutrinos. The neutrino burst from the core collapse would arrive at Earth several hours before the visible light from the explosion. This is because the neutrinos are produced the instant the core collapses, and they travel through the star almost unimpeded, escaping in seconds. The light from the explosion, however, has to work its way through the star's massive envelope, which takes hours. This was exactly what happened with supernova 1987A. Neutrino detectors registered the burst roughly 3 hours before the supernova became visible in telescopes. If Betelgeuse were to go supernova, neutrino detectors around the world would sound the alarm hours before anyone saw anything in the sky. We would have a few hours of warning, enough time to point every telescope on Earth and in orbit at Betelgeuse and capture the explosion from the very first moment. Light breaks through the surface. Now let's talk about what we would actually see from Earth when Betelgeuse explodes, because this is what most people really want to know. Betelgeuse is roughly 550 light years from Earth. That's far. Very far by human standards. But by cosmic standards, especially for a supernova, it's remarkably close. Most supernovae we observe are in other galaxies, millions or even billions of light years away. A supernova at 550 light years would be the closest observed supernova in centuries, probably the closest since Kepler's supernova in 1604, which was roughly 20,000 light years away. Betelgeuse would be dramatically closer than that. At 550 light years, a Betelgeuse supernova would be spectacularly bright. Estimates vary depending on the exact energy of the explosion and the angle of the blast, but most calculations suggest it would reach an apparent magnitude of roughly -12 to -13. For comparison, the full moon has an apparent magnitude of about -12.7. So Betelgeuse's supernova would be roughly comparable to the full moon in brightness, possibly a bit dimmer, possibly a bit brighter depending on the details. It would absolutely be visible in broad daylight. During the day, you would see a brilliant point of light in the sky, shining through blue sky and clouds, brighter than anything except the sun itself. At night, it would cast visible shadows. The constellation Orion would be transformed. Where Betelgeuse's familiar reddish glow once sat, there would be an intensely brilliant point of light, bluish-white at peak, outshining everything else in the night sky, except the moon. Would it be dangerous? This is the other question people always ask, and the answer is reassuring. No. A supernova at 550 light years would pose no threat to life on Earth. The dangerous effects of a supernova, intense gamma radiation, X-rays, and the physical blast wave of expanding debris dissipate enormously over distance. To pose a serious threat to Earth's atmosphere, specifically to damage the ozone layer enough to affect life, a supernova would need to occur within roughly 50 light years. Some estimates put the danger zone even closer, at about 25 to 30 light years. Betelgeuse is more than 10 times farther away than the outer edge of any credible danger zone. By the time the supernova's radiation reaches Earth, after traveling 550 light years, it will have spread out over such an enormous volume of space that its intensity will be negligible from a biological or atmospheric standpoint. The neutrinos would arrive first, billions of them passing through your body without doing anything. You wouldn't feel them, you wouldn't notice. Then the light would arrive, and for a few weeks, you'd have an extraordinary new feature in the sky. That's it. No mass extinction, no atmospheric damage, no radiation sickness. Just a beautiful, awe-inspiring light show, visible to everyone on the planet. The most dramatic astronomical event any living human would ever witness, and completely safe to watch. And while a Betelgeuse supernova would be unprecedented in the modern era, it would not be the first time human beings have witnessed a star explode. We know this because it has happened before, and the records those observers left behind, some written, some carved in stone, have become invaluable to modern astronomy. The most famous historical supernova occurred in the year 1054. Chinese astronomers recorded the sudden appearance of a brilliant new star in the constellation we now call Taurus. They called it a guest star, a term they used for any celestial object that appeared where none had been before. According to their records, this guest star was visible in broad daylight for 23 days. It was bright enough to be seen even when the sun was in the sky, shining as a clear point of light against the blue daytime background. At night, it was brilliant, far outshining every other star. After those 23 days, it gradually faded from daytime visibility, but remained visible at night for nearly 2 years, before finally dimming beyond the reach of the naked eye. Japanese astronomers recorded the same event independently, confirming the Chinese observations. There is also evidence that Native American groups in the American Southwest recorded the event. Pictographs found in Chaco Canyon in New Mexico and at other sites appear to depict a bright star near a crescent moon, which matches the astronomical configuration of the supernova's position relative to the moon on the morning of July 4th, 1054. If this interpretation is correct, then people on opposite sides of the planet, with no communication between them, all looked up at the same sky and recorded the same extraordinary event. Today, when we point our telescopes at the location where Chinese astronomers saw that guest star, we find the Crab Nebula, a beautiful expanding cloud of gas and filaments, roughly 11 light years across, still glowing nearly 1,000 years after the explosion. At the center of the Crab Nebula sits a pulsar, a rapidly spinning neutron star about 12 miles across, rotating roughly 30 times per second. This is the remnant of the star that exploded in 1054, the neutron star that was born in the core collapse, that Chinese astronomers recorded as a bright new light in the sky. The Crab Nebula is one of the most studied objects in all of astronomy, and its existence is direct physical proof that supernovae leave behind both expanding remnants and compact stellar corpses. When Betelgeuse explodes, the same thing will happen. A nebula will form, a neutron star or black hole will remain, and the debris will expand outward for thousands of years, glowing as it plows into the surrounding interstellar gas. In 1572, another supernova appeared. This time, it was observed by the Danish astronomer Tycho Brahe, who studied it so carefully and published such detailed records that it became known as Tycho's supernova. Tycho described a new star in the constellation Cassiopeia that rivaled Venus in brightness and was visible during the daytime. He tracked its brightness over months as it gradually faded. His meticulous observations proved that the object was far beyond the moon, shattering the ancient Aristotelian belief that the heavens were unchanging and perfect. The heavens could change. Stars could appear and disappear. The cosmos was not static. Just 32 years later, in 1604, another supernova appeared. This one was observed by Johann S. Kepler, and it became known as Kepler's supernova. It appeared in the constellation Ophiuchus and at its peak rivaled Jupiter in brightness, making it a striking naked-eye object that dominated its region of the sky at night. Kepler tracked it for over a year as it slowly faded. This was the last supernova observed in our own galaxy with the naked eye. That was over 400 years ago. Since 1604, no supernova has been detected in the Milky Way by human observers. We've observed thousands of supernovae in other galaxies using telescopes, but none in our own galaxy. We are statistically overdue. Astronomers estimate that supernovae occur in the Milky Way roughly once or twice per century, which means several have almost certainly happened in the last 400 years. But they were either too far away, too obscured by interstellar dust, or too faint to be noticed. A Betelgeuse supernova would end that 400-year drought spectacularly. It would be closer than Tycho's supernova, closer than Kepler's supernova, and potentially brighter than both. It would be the first supernova visible to the naked eye from our own galaxy since the invention of the telescope, since the invention of radio, since the invention of neutrino detectors, since the launch of space-based observatories covering every wavelength from radio to gamma rays. for the first time in history, a supernova in our galaxy would be observed with the full arsenal of modern astronomical instruments. The scientific payoff would be extraordinary. We would learn more about supernova physics from a single nearby event than from decades of observing distant supernovae in other galaxies. And we are prepared for it. The modern astronomical community has built a system specifically designed to catch the next galactic supernova as early as possible. It's called S-News, the Supernova Early Warning System. S-News is a network linking neutrino detectors around the world, including Super Kamiokande in Japan, IceCube at the South Pole, and several others. The system works on the principle we discussed earlier. Neutrinos from a core collapse arrive hours before the visible light. When multiple neutrino detectors simultaneously register a burst consistent with a supernova, S-News automatically sends an alert to observatories worldwide, telling them to point their telescopes at the source. The goal is to capture the very first light from the explosion, the moment the shockwave breaks through the star's surface, which has never been observed from a nearby supernova. The data from those first hours would test our theoretical models of core collapse with unprecedented precision. There is also something worth imagining about the long aftermath. The supernova wouldn't just produce a brief flash and then vanish. The expanding debris cloud, the supernova remnant, would grow over centuries and millennia. In the years following the explosion, a faint glowing nebula would appear around the site where Betelgeuse used to be, visible through telescopes. Over decades and centuries, that nebula would expand, growing larger and larger as the ejected material, traveling at thousands of kilometers per second, plowed into the surrounding gas. Within a few thousand years, the remnant could span several light years across. A ghostly, glowing shell of filaments and knots, much like the Crab Nebula, but potentially much larger, because Betelgeuse has far more mass to eject. Future generations of astronomers would study this remnant the way we study the Crab Nebula today. They would watch the debris interact with the surrounding interstellar medium, forming shock fronts and turbulent structures. They would measure the chemical composition of the ejected material, cataloging exactly how much carbon, oxygen, silicon, iron, and heavier elements Betelgeuse contributed to the galaxy. They would search the center for the neutron star or black hole left behind, measuring its spin, its magnetic field, its emissions. The supernova remnant of Betelgeuse would become one of the most studied objects in the sky for centuries to come. And for anyone alive when it happens, there will be a subtler change. A permanent one. Orion will never look the same. The familiar pattern that humans have gazed at for tens of thousands of years, the three belt stars, the bright shoulders and feet, will be altered forever. Betelgeuse, the bright reddish star marking the hunter's upper left shoulder, will be gone. In its place for a few weeks, there will be something far brighter. And then, as the supernova fades, there will be nothing. Just a faint nebula visible through telescopes where a bright star used to be. The constellation will have a gap, a missing piece, a reminder that the night sky is not eternal, that stars are born and stars die, and that even the most familiar patterns in the heavens are temporary arrangements, destined to change. There is one thing worth mentioning. Betelgeuse is roughly 550 light-years away, which means the light we see from it tonight left the star about 550 years ago. If Betelgeuse's core collapsed today, right now, this very moment, we wouldn't know for 550 years. The neutrinos and the light from the explosion would begin their long journey across space, traveling at the speed of light, and would arrive at Earth around the year 2576. Conversely, it's possible that the core has already collapsed. Perhaps the supernova occurred 100 years ago, or 200 years ago, and the light is currently en route to us. We have no way of knowing. There's no way to see what Betelgeuse looks like right now. We can only see what it looked like 550 years ago. The star might already be gone, replaced by an expanding cloud of debris and a tiny neutron star, and we wouldn't know until the light reaches us. This uncertainty is inherent to astronomy at these distances. Every star you see in the night sky is a window into the past. You're not seeing the star as it is right now. You're seeing it as it was when the light left it. For nearby stars, the delay is only a few years. For Betelgeuse, it's centuries. The Betelgeuse you see tonight is Betelgeuse as it was during the Italian Renaissance. Whatever is happening at the star right now is hidden from us, locked behind a wall of distance that light itself needs centuries to cross. Let's step back now and think about what all of this means. Not just the science, but the bigger picture. We started this journey with a simple observation. Betelgeuse is big. And from that single fact, we traced a chain of cause and effect that connects size to instability, instability to fuel exhaustion to core collapse, and core collapse to one of the most violent events in the cosmos. Scale and death are not separate topics when it comes to stars like Betelgeuse. They are the same topic. The enormous size of this star is not incidental to its fate. It is the cause of its fate. A smaller star, a star like the Sun, will never die this way. The Sun will exhaust its hydrogen, expand into a red giant, shed its outer layers, and leave behind a quiet white dwarf that will cool slowly over trillions of years. No explosion, no supernova, no neutron star or black hole. The Sun doesn't have enough mass to build an iron core. It will never reach the Chandrasekhar limit. It will never experience core collapse. The Sun's death will be gentle because the Sun is small enough for a gentle death. Betelgeuse doesn't have that option. Its mass guaranteed from the moment of its birth that it would live fast, burn through its fuel at an extraordinary rate, swell to dimensions that swallow planets, and die in a catastrophic explosion. There was never another possibility. The physics was set 8 to 10 million years ago when the star first ignited. Everything since then has been an inevitable unfolding of the consequences of that initial mass. More mass means stronger gravity. Stronger gravity means higher core temperatures. Higher core temperatures mean faster fuel consumption. Faster fuel consumption means a shorter life. A shorter life means a more dramatic death. This chain is unbreakable. It applies to every massive star in the universe, and it applies to Betelgeuse. This is why the title of our exploration tonight connects size and death. Stars this big don't die quietly because they can't. The very mass that makes them enormous is the same mass that drives them toward catastrophe. A red supergiant is not just a large star. It is a star in crisis. A star whose core has already failed to sustain itself on its primary fuel and is now burning through increasingly desperate alternatives at an accelerating pace. The bloated, swollen exterior that we observe through our telescopes is not a sign of health. It is a symptom of a star that has lost its equilibrium. A star that is struggling to hold itself together as the energy sources at its center shift and change and diminish. And yet, there is something magnificent about this. Betelgeuse's death, whenever it comes, will not be meaningless destruction. It will be an act of creation. The supernova will scatter into space all the elements that Betelgeuse forged during its life: carbon, oxygen, silicon, iron, and all the elements heavier than iron that will be created in the explosion itself: gold, platinum, uranium. These elements will mix with the interstellar medium, enriching the gas clouds from which future generations of stars and planets will form. Our own solar system was built from the debris of earlier supernovae. The heavy elements in Earth's crust, the iron at its core, the carbon in every living organism, the oxygen in every breath you take, all of it was produced by massive stars that lived and died billions of years ago. You exist because stars like Betelgeuse exploded in the distant past. Every rocky planet, every ocean, every molecule of breathable air in the universe exists because a massive star once died violently enough to scatter its elements across space. Without supernovae, the universe would contain nothing but hydrogen, helium, and trace amounts of lithium. No carbon, no oxygen, no iron, no water, no complexity of any kind. The periodic table beyond its first few entries is a monument to stellar violence. Betelgeuse will continue this cycle. When it explodes, it will seed this region of the galaxy with the raw materials for new stars, new planets, and potentially new life. Billions of years from now, a planet might form from a cloud of gas enriched by Betelgeuse's remains. On that planet, if conditions are right, life might arise, and that life might eventually look up at its own sky and wonder about its own place in the cosmos, never knowing that the atoms in its body were once part of a bloated red supergiant that a long-vanished species on a distant world called Betelgeuse. Tonight, if the sky is clear, step outside and look south toward Orion. Find the 3 stars of the belt. Then look up and to the left. You'll see it. A reddish-orange point of light glowing softly against the blackness. That's Betelgeuse. A star 700 times wider than the Sun. A star so enormous that if placed at the center of our solar system, the Earth would be deep inside it. A star burning through the last stages of its fuel, building an iron core that will one day trigger its own destruction. It looks peaceful up there, calm, just another dot of light among thousands. But now you know what it really is. You know how large it is. You know why it's that large. You know what's happening inside it right now, deep beneath those bloated outer layers where shells of different elements burn in nested rings, each one hotter and faster than the one above it. You know that the iron core is growing, and you know what happens when that core reaches its limit. Betelgeuse is a clock. It has been ticking since the moment it was born. Every hydrogen atom that fused into helium was a tick. Every helium atom that fused into carbon was a tick. Every shell that ignited, every fuel that burned, every element that accumulated in the core, all of them ticks on a clock that is counting down to an event so powerful it will briefly outshine billions of suns. We don't know when the final tick will come. It might be tomorrow. It might be 1,000 years from now. It might be 100,000 years. But it will come. The physics demands it. And when it does, a star that took 8 million years to build will destroy itself in seconds. A point of light that has graced Orion's shoulder for all of recorded human history will be replaced by a blinding brilliance visible in the daytime sky. And then it will fade. The light will dim over months. The debris will expand into a beautiful glowing nebula. And at the center, A tiny neutron star, or perhaps a black hole, will sit quietly in the dark, the last remnant of something that was once magnificent. Betelgeuse is not just a star. It is a story about how the universe builds and destroys and rebuilds. About how mass determines fate. About how the biggest things in the cosmos are also the most fragile, burning too fast, living too short, dying too violently. And about how that violence, that destruction, is the very thing that makes new worlds and new life possible. The death of Betelgeuse, whenever it comes, will not be the end of the story. It will be the beginning of something new. New stars, new planets, new possibilities, all born from the ashes of a giant that burned too bright and too fast and couldn't hold itself together. Look up tonight. Betelgeuse is still there, still glowing, still burning, still counting down, and every photon that reaches your eye has been traveling for 550 years, carrying a message from a star that was already ancient and already dying when that light began its journey. You're seeing the past. You are watching a giant in its final act. And one day, perhaps not in your lifetime, perhaps centuries or millennia from now, the show will reach its spectacular conclusion. When it does, Betelgeuse will remind the entire world of something we too easily forget. That the universe is not static. That stars are born and stars die. That the night sky is not permanent. And that the atoms that make up everything we know, everything we are, were once inside stars just like this one. Stars that lived, stars that burned, stars that died so that we could exist. That's the true scale of Betelgeuse. Not just its physical size, though that alone defies comprehension, but the scale of what it means. A single star, visible to the naked eye, connecting us to the deepest processes of the universe. Birth and death, creation and destruction, the past and the future, all of it written in the reddish glow of a dying giant in the shoulder of Orion.